Thank you very much, John. I'm not sure I'll possibly live up to what you expect, but I'll give it a try. Sounds like everybody can hear me. Is that right?
Yes.
Okay. So this is the last of the 7 Millennium talks and concerns a problem which had its origin in attempts to understand the distribution of prime numbers among the integers. So to begin with, what I'm going to try to accomplish here is a crash course in basic prime number theory. Let me start with this definition. I think that looks at least in focus on top, I think, for everybody. Okay. So before we get to the technical details of the Riemann hypothesis, we need to lay a little groundwork. And these ideas really go back to the ancient Greeks, who formulated the notion of a prime number and proved some basic theorems about it about 2,300 years ago. These are results which are recorded, for example, in Euclids Elements and remained a basic part of mathematics well into the Middle Ages. So by a composite number in this talk, I understand a positive integer n greater than or equal to 2, which can be factored as a product of 2 positive integers, a and b. And the important thing is that in this factorization, a and b have to be smaller than n. So you're decomposing a large number n as a product of 2 smaller numbers. But of course, some numbers don't have the property, and those are the prime numbers. And well, from this definition, probably everybody in the audience can start to make a simple table of primes. 15 obviously is composite because you can readily factor it as 3 times 5, but 17 doesn't have that property. You just have to think about the basic multiplication table to see that. 99 is another composite number because it has a factorization into 2 smaller positive integers, 9 times 11. Of course, 99 is also 1 times 99, but that one doesn't count. Right? We have to factor them into smaller numbers always. So when you try to factor 101, you find that it's not possible. And so 101 is another prime number. Now, probably most of you haven't bothered to sit down and look at lists of prime numbers or examine them under a microscope or in any other way for that matter. So I made a brief list here of the first 200 primes that you can look at just to begin to get a feel for how they work, so to speak. This little quote over here from Ingham's text is also something that I've always liked. I think the last sentence is particularly apt. The series of prime numbers exhibits great irregularity of detail. But if you kind of stand back and look at it from a distance, you see that it does have a certain, well, rough regularity that's hard to pin down and articulate, but nevertheless leads to the possibility that perhaps some sort of theory could be developed about these numbers. If you take a look at the first 200 primes, I think you'll probably, if you've even never seen this sort of mathematics before, you'll certainly come to the conclusion that it's hard to predict easily which numbers are going to be primes and which ones aren't. For example, if you take a look at this row right here, you see a list of primes from 571 to 647. You could puzzle over it for a long time and not see any kind of pattern that would allow you to predict the next row, for example. I mean, if you think about it, really impossible. But even if you've never thought about it and you try to puzzle out this sort of sequence and try to see what causes it to happen and which numbers are prime, it's just really nothing that you can do except to go back to the original definition and ignore the whole list and just, if you want to find the next prime, these aren't going to be a lot of help. The first few primes might help you, but the ones that come just before it aren't really going to enter in. If you extend the table substantially, so here's a list of prime numbers that are a lot further out. This list starts with the 1/billionth prime number. You'll see that, again, if you examine the table closely, there's a lot of irregularity. For example, right in here, you see 2 prime numbers that are separated by only 2. But I think these down at the bottom are separated by 64. And these are consecutive primes, I should add. Okay, I mean, this is the 1 billionth prime, and this is the 1 billion and first prime, and so forth. And it's just generally true. If you look through this list, you're going to have a hard time, again, predicting what's going to happen based on this sort of knowledge. So in detail, the primes behave in a very irregular way. But on the other hand, you know, there aren't gaps of 1,000 here, or there aren't any other sort of eccentric pattern that you can really look at. One might sort of say that the primes behave in a random way, well, except when they obviously do not. Let me clarify that a little bit. You might think, if you've never seen this sort of subject before, that half the primes would be odd and half the primes would be even. Well, but of course that's really obviously not possible because the even primes are divisible by 2, so 2 is the only even prime. Well, you might think that the primes divide evenly into the residue classes 1 mod 4 and 3 mod 4, meaning about half the time when you divide a prime number by 4, the remainder is 1, and the other half of the time when you divide a prime by 4, the remainder is 3. In fact, that can be made into a theorem. And that's more or less correct, that they do randomly distribute into residue classes in that fashion. In fact, I'll say more precisely how that works later on. Now, let me switch now to some more constructive results about primes. So I sort of hesitate to prove theorems here, but these theorems are about 2,300 years old, so somehow I feel like we can handle this. So this first lemma tells us the important fact that every integer n greater than or equal to 2 can be written as a product of prime numbers. And the proof is almost proves itself, really. Suppose there were some positive integer, capital N, which is not a product of prime numbers. Well, then there'd have to be a smallest integer with that property. And if we now call that capital N, then you immediately see that capital N cannot itself be a prime. Otherwise, you just write it as capital N, and that'd be it. If it's not a prime, then it has to factor into a product of two smaller numbers, a and b. Since a and b are smaller than n, and n was the smallest prime, the smallest integer, I should say, which can't be written as a product of primes, it must happen that a and b can be written as a product of primes. Okay, so we write a and b out here, as I have, a as p1 times p2 through pl, so those are primes. And b is also, of course, smaller than capital N, so you can write that out as primes, q1, q2 through qm. Well, then obviously all you have to do is just write a and b together, and you've written capital N as a product of the p's times the q's. So in fact, we reach a contradiction. Capital N can be written as a product of primes. And so the set of integers which cannot be written as a product of primes must be empty. Okay? And so that's essentially the proof of this lemma. Now, from this lemma, which, as I say, goes back to the ancient Greeks, I mean, the notation and the terminology, of course, is obviously modern. But from this proposition, one can prove the following important theorem, that the set of prime numbers is infinite. And the proof here is essentially the one that was given by Euclid. Suppose, contrary to the statement of the theorem, that you thought p1, p2, and pn was a complete list of all prime numbers. Well, you could multiply p1, p2, and so forth together, and then you'd have a number that was divisible by all the primes. So if you add 1, and you form the number capital Q, then you see the number capital Q could not be divisible by any of the primes on your list, because you're always going to get the remainder 1. Well, but the lemma tells us that all numbers, including Q, can be written somehow as a product of primes. But the primes on your list, P1 through Pn, won't work. So therefore, there must be other primes. So the conclusion here is that no finite list of primes will ever do. Thus, the set of primes must be infinite. We can take a hint from these results and try factoring integers in hopes of maybe finding some clues about how the primes work and how they distribute. Again, I suppose a general audience doesn't contain a lot of people who do this sort of thing, but, well, here are some examples of factorizations of some numbers that were selected by a very sophisticated random process to be odd numbers and not to be generated from any particular preconceived idea of what numbers I wanted to appear here. These are just random 40-digit numbers. And you can see that, well, the theory tells us that there should be about 4.5 prime factors for each number, and that's approximately what's happening. Of course, there's some variation around that amount. But you know, you can stare at this too, just like a table of prime numbers, and you don't really get much feel for what could be said other than the fact that there seems to be a certain randomness or irregularity which perpetually seems to appear when you work with prime numbers, factor integers into primes, measure how big they are, and so forth. After I made this, it occurred to me that maybe it wasn't necessary to use any kind of sophisticated random process, so I tried this as an exercise just to factor some non-random numbers. And so to be simple-minded about it, I just chose the digits to have an obvious pattern. And here's some examples of 40-digit numbers, which obviously don't appear to be random, and their factorizations. And you see, it really didn't matter, right? You can't make or I don't think it's very easy to make a special factorization pattern of any sort by choosing the digits. You really, I guess the bottom line is you can't tell if a number is prime by looking at its digits. If the digits look sort of random and mixed up, it might be prime or it might not be. The factorization of the integer tends to have, for 40-digit numbers, about 4.5 to 5 prime factors on average. But even if you were to take non-random numbers of this shape, the truth still is that the number of prime factors that appear seems to be about 4.5 to 5. There's some variation around that, of course. This first number has quite a bit more, but here's one with only 3. Okay, let me go on now to a further important theorem that's also won't be given with a proof here, but a further important theorem which comes from Euclid's Elements. This goes a little bit beyond the lemma that I had put up here before and tells us that not only does each integer n greater than or equal to 2 split up as a product of prime numbers, but this essentially happens in only one way. And that turns out for an interpretation that ultimately leads to the Riemann hypothesis to be an absolutely essential observation. So you could express it in several ways. For example, as I've indicated here, the integer n can be written as a product of distinct prime numbers p1, p2, p3, and then I've introduced some exponents, e1, e2, and so forth. So the prime p1 appears in the factorization e1 times, and so can be written in this fashion. And to make sure that this is unique and the only way to do it, so to speak, you would arrange the primes in increasing order. So let p1, say, be the smallest of the primes that occur in the factorization of n, and p2 the second smallest, and so forth. And then if you enforce that restriction on the factorization, you find that it's unique. That's going to come up later on in a crucial way. Now, one final remark here before we look at other matters. One might ask why exactly it is that mathematicians, or number theorists in particular, would be interested in primes. There's probably some intrinsic reasons about the irregularity, the essential beauty of the whole process that causes them to unfold. But they also appear sometimes unexpectedly in basic problems. For example, let's consider this problem. Suppose we have a positive integer, capital N, and we'd like to write capital N as a sum of 2 squares. You may remember that in Fernando Villegas's talk earlier in the spring, something of the same sort appeared. I think in his case he wanted capital N to be a prime and asked this question. But this is a slightly different twist on the same basic theme. Suppose capital N is just some large positive integer, and we'd like to know if you can write it as a sum of 2 squares. Well, you know, at first, if you've never seen this sort of thing before, I think you might suspect that prime numbers don't enter into the problem, because after all, you're adding things together, right? You're taking x and multiplying it by itself to form x squared, and you're doing the same thing to y. But then when you add them together, there's nothing about being a prime that involves addition. At least that appears to be the case from the definition. And yet, to solve this problem, the critical step is to take the integer capital N, and here I've illustrated it with this moderately large number here. The key step is to take the positive integer n and write it as a product of prime numbers. And then what you do is you look through the odd primes, and you pick out those that have remainder 3 when you divide them by 4. In other words, they're congruent to 3 mod 4. And in this particular case, 3 has that property, and 23 has that property. But the other odd primes, they're all congruent to 1 mod 4. OK, second step. You take a look at the exponent. So little 4 here and little 2 there. And if those exponents are even on the primes which are congruent to 3 mod 4, then there must be a way of writing n as a sum of 2 squares. But if any of these exponents on the primes 3 and 23 in this example would be odd, then it's not possible to write n as a sum of 2 squares. So in spite of the problem involving addition, primes and the decomposition of n into prime factors plays a crucial role in the resolution of the problem. In fact, we could go on, but I won't, and even describe how you find 2 integers, as I've done down at the bottom here, with the property that the sum of their squares is equal to the original integer. You can count the number of ways of doing this. It's a slightly complicated procedure, but you can count the number of ways of doing this, given the prime factorization initially for the number capital N. Now, eventually I want to get to a little more modern history here, since these observations, although this discussion of writing an integer as a sum of 2 squares is more or less known to Fermat in the Middle Ages, the theorems that I've quoted all go back to the ancient Greeks. Here, however, are some problems about prime numbers, which maybe some of you have seen before and are of a little bit more modern origin. The first one is the famous Goldbach problem. And I've quoted here, with translation, the actual letters that were exchanged between Goldbach and Euler in 1742. The question here is, well, ultimately, can every even integer greater than or equal to 4 be written as a sum of 2 prime numbers? As far as we know, this appears to be correct. Euler, in 1742, says, every even integer is a sum of 2 primes. I regard this as a completely certain theorem, although I cannot prove it. Well, no one else has proved it either in the meantime. What is known today, due to very sophisticated sieve methods, is that every even integer capital N can be written as a sum of 2 numbers, one of which is a prime, and the other one has at most 2 prime factors. That's pretty close, but it's actually about 10% of the way up Mount Everest. The next step is much, much harder than all the steps that have gone before, you might say. Another problem, which mathematically turns out actually to involve many of the same tools in attempts to resolve it, is the so-called twin prime problem. So if you look at tables of primes, you quickly observe that it seems that as far as they go, there are examples that occur pretty regularly where p is a prime and then p plus 2 is also a prime. So this is called a twin prime. And it's an old problem to prove that there are, in fact, infinitely many twin primes. But this is still unsolved today. The best we know is somewhat analogous to our knowledge about the Goldbach problem. It's known that there are infinitely many primes p such that p plus 2 has at most 2 prime factors again. But again, the story is that while that's the result of many ingenious ideas, to make the next number a prime, so to make p plus 2 actually a prime is again a big leap, probably greater than all the work that had been done previously. A third problem, as I'll just mention briefly, and this type of problem in number 3 here can be generalized. Well, in fact, they can all be generalized in various ways. In problem 3, I've written down an irreducible polynomial, x squared plus 1, and asked if there are infinitely many primes that can be written in that form. So x would have to be an integer, capital N. So in other words, are there infinitely many primes of the form n squared plus 1? Again, this is an unsolved problem today. But what is known about it is somewhat similar to what I described about the other problems. Finally, the fourth problem here is actually going to occupy me for much of the rest of the talk. This is a less specific problem, but now comes closer to what ultimately the Riemann hypothesis is about. I'm going to define pi of x to be the number of primes less than or equal to x. So you pick x, maybe x equal 100. You count the number of primes up to x, and that's the value of pi of x. So in between two integers, pi of x is constant, of course. So its graph has a jump at a prime, and then it's flat until you come to another prime, and then it jumps up again, and so forth. Now, because the primes behave in an irregular way, pi of x behaves in a pretty irregular way, too. And yet, there are some things that can be said about it. We'll take a look here. Well, in fact, maybe I'll just leave it for a minute or two. We'll take a look at the graph of pi of x and also some possible approximations to pi of x that were found, well, the most important one really was found by Gauss. So, roughly speaking, the objective here is to try to find some simple, let's say, calculus-type functions which give a good approximation to pi of x. But I'm leaving as a little vague what exactly that means. To some extent, you have to let the mathematics that unfolds guide you to how this is actually supposed to be interpreted. Okay, now, let me begin to describe some tools that have been discovered for use in prime number theory. I think perhaps the most important one is what is called the Euler product formula. Now, if you're not used to looking at this sort of thing, this may seem, well, hard to look at. But let me see if I can just help the process a little bit by explaining how it works, because this is a really, truly ingenious discovery. To my way of thinking, one of the most beautiful identities in mathematics. This is a mechanism for encoding the fundamental theorem of arithmetic that I spoke about before as an identity between two functions. Now, when Euler did this, this function, which is defined by the infinite series up here, is a function of the real variable s. And in order to make sure that that infinite series converges and so actually defines a function of s, it's necessary that s be greater than 1. It turns out that this very same function can be defined as a product over prime numbers. Well, it's a little more complicated than that. Here we have a product of more infinite series. But you'll notice this expression inside the first pair of parentheses depends on the first prime number 2. And the next expression depends on the next prime number 3. And then 5 and 7 and 11. And 13 and 17 and so forth come next. So in effect, these functions of s that are appearing here depend on the prime numbers. Now, why is this an identity? Well, let's just see how you'd form the number 1 here. Well, obviously, if you're going to multiply all these things together, you're going to take the 1 here and the 1 there and the 1 there and so forth, and just take 1s from all the infinite series that are occurring in here. How do you get 1 over 2 to the s? Well, that's probably clear by now. You take 1 over 2 to the s. 2 is a prime, and it appears here. And then you take the 1 in all the other series. Let's skip up to 1 over 6 to the s. Well, you think of the prime factorization of 6. It's 2 times 3. So therefore, you take a look in the first series, and you take 1 over 2 to the s. And then you take 1 over 3 to the s. Now you've got 1 over 6 to the s. And then you take 1s all the rest of the way. How about 1 over 9 to the s? Well, 9 has a prime factorization into 3 squared. So you take 1 and then 1 over 3 squared to the s is right here, and then 1s from all the other products. Well, is it possible that you could get 1 over 9 to the s in some other fashion? No. The fundamental theorem tells us there's only one way to factor 9, or indeed any other integer greater than or equal to 2, into prime factors, or, as is happening here, into primes to powers. That means that the numerators in these fractions are all going to be 1s. You see, if there were 3 ways of producing 1 over 6 to the s, then each of those 3 ways would produce 1 over 6 to the s, and I'd add them up, and I'd get 3 over 6 to the s. But that's not how it works. So what's happened here is that we've encoded the fundamental theorem of arithmetic into a function. And if we write it a little differently and take this infinite series and write it down here as a sum with the index n, and we can sum up these infinite series inside here, and they sum up to 1 minus 1 over p to the s to the power minus 1, it turns out. And then we can introduce the capital pi expression, which indicates that you form a product over all these expressions as p runs over the prime numbers p. We see a fantastic identity. Now, let me explain why this is so incredible. Let's suppose we want to solve a problem about prime numbers. We take our problem about prime numbers and we try to reformulate it as a problem about this function of s. That should be a reasonable thing to try to do because, after all, the primes occur in this function. Now, normally that would go nowhere because in order to find out any useful facts about this function, apparently you got to know about primes. But it's not so in this particular situation because you can trade in that representation and replace it by this representation over here because they define the same function. Now, there's no primes involved in the description of the function in this fashion. So, at least in principle, you should be able to learn anything you want about this function without knowing anything about primes by using that representation. This is a piece of mathematical magic, in a sense, that this should be able to happen because it's the key to discovering theorems about primes. There's only one little problem, however, that occurs. It turns out that while you now have an expression involving functions of s, it's very tricky to extract prime number theorem or prime number information out of these functions when s is restricted to be greater than 1. And that restriction appears to be unavoidable because if s is not a real number bigger than 1, well, they don't converge, and so they don't define any kind of a function. So while this is a very ingenious idea, it awaits one more good idea, and that's what Riemann did. Euler was able to extract something out of this, though. If you take the limit as s approaches 1, some of you with a little knowledge of calculus will probably be able to work out the proof that the sum of the reciprocals diverges. The sum of the reciprocals of the primes diverges. So that's another proof that there are infinitely many primes. But of course, it says more than that. There are infinitely many squares, for example, but the sum of the reciprocals of the squares converges. So it means that there are a fair number of primes in some sense. Now, the next great moment in prime number theory is due to Legendre, but really more importantly to Gauss. Gauss experimented with tables of prime numbers. And after a good deal of thought and work and experimenting, sort of seat-of-the-pants mathematics, he decided that the probability of a number being prime if the number is out at about n is roughly 1 over log n, roughly. And that motivated him to sum 1 over log n, or, as I've done here in the modern way of approaching this problem, to integrate 1 over log t from 0 up to x, and take that as a rough approximation of pi of x. Now, this might look a little funny here to split up the limit in this way. This is a Cauchy principal value type of integral. You shouldn't be too put off by the limit and the funny way of looking at it if you haven't seen this, for example, in a calculus course. It's just taking into account the fact that 1 over log 1 is 0, and so I have to treat that point a little bit carefully here. Both Gauss and Legendre were a bit vague about what they meant by an approximation to pi of x, but it seems pretty clear that they both thought, in Gauss's case, that pi of x over Li of x should approach 1. Li of x is called the logarithmic integral of x. It turns out that the logarithmic integral and x over log x are essentially asymptotic to one another anyway. So if you're only going to be interested in the value of these limits, it doesn't make too much difference which one you choose. But in retrospect, it turns out that Li of x is an excellent approximation to pi of x. Here's a graph in which the top function is the logarithmic integral of x. So that's a kind of calculus level function that increases nice and smoothly. And the graph below it, which is a step function, of course, is pi of x. And you'll see that it does indeed, at least in the early going, appear to be a pretty good approximation. Here's the same information a bit further out. So this is the primes between 10,000 and 10,300. And the line above it, of course, is the logarithmic integral of x. I guess probably most of you would conjecture, if you were asked, that perhaps Li of x is always bigger than pi of x. All the numerical evidence seems to indicate that's probably true. And you'd be in good company. Gauss thought it was, and even Riemann sort of said vaguely that there were reasons why the logarithmic integral of x was probably bigger than pi of x, but it isn't so. Littlewood proved in 1914 that, in fact, the logarithmic integral graph and the pi of x graph oscillate back and forth infinitely often. The first time pi of x gets above the logarithmic integral of x, however, is pretty big. Today we know it's out around 10 to the 370th. So it's way out beyond the range of computers. Here's another way of looking at the issue. This is a pretty extensive table giving the values of pi of x and the logarithmic integral of x. The bottom number here is 10 to the 20th, and that, as of a few years ago at least, was as far as pi of x had actually been calculated. And if you take a look at this second table here at the bottom, where I've given the difference between Li of x and pi of x, you can see that, well, roughly speaking, the difference between the logarithmic integral of x and pi of x is about square root of x. You know that because the square root of a 20-digit number is about a 10-digit number, and so forth. And the number of digits here is usually less than or equal to half the number of digits over on the left. So that indicates that Li of x and pi of x are pretty close together. Now, let me skip now to the work of Chebyshev. Who considered also the problem of good approximations. And I think I even have a picture of him. Probably stared at Ingham's quote long enough here. So anyway, there was Chebyshev. Now, Chebyshev introduced another good idea. Instead of counting the number of primes up to x, instead of working with pi of x, Chebyshev introduced a weighted prime counting function, which he called psi of x. Well, roughly speaking, instead of counting 1 each time you come to a prime, you count the logarithm of the prime. There's another little wrinkle, too. If you come to a prime power, a prime cubed, you count the logarithm of the prime. You throw away the cube, so to speak. This simplifies matters because it turns out that if you have a result that tells you that pi of x is approximately the logarithmic integral of x, then you also know that psi of x is approximately x. X is a simpler function to work with than the logarithmic integral of x. And so this is a desirable idea. It's also desirable for another reason. This contains the same magic that occurred in Euler's identity. This is an identity up at the top here that is satisfied by the psi function. And you'll notice there's prime number information on the left-hand side, but there's no prime number information on the right-hand side. So in principle, you should be able to extract information about psi by this identity because you can analyze the right-hand side without knowing anything about primes. Indeed, the right-hand side, if you look at it, is the logarithm of the integer part of x factorial. And there are good estimates for that. And, well, Chebyshev was aware of these things and turned the crank, so to speak, that comes from that formula, and was able to give estimates for the size of psi of x. And therefore, as I indicated in the previous remark, he made an estimate for pi of x down here. He showed that it was in between two multiples of the logarithmic integral of x. And he also showed something else with this machinery. If the limit pi of x over Li of x exists at all, then it has to be 1. Of course, you can't deduce that from this inequality, but by other means, Chebyshev was able to show that if the limit exists, it has to be 1. Okay, now we come sort of closer to the main objective here. And let me let Chebyshev give way to Riemann. So Riemann had the excellent idea to reconsider Euler's basic formula. His good idea was to replace the real variable s, which has to be greater than 1, with a complex variable. The real part of s is now a complex number. The real part of s he called sigma. The imaginary part he called t. This slightly odd notation, however, has stuck and is still used. And this turns out to have important implications because, as I said, it's very hard to make use of this wonderful identity if s is just a real number bigger than 1. You can do something with it, but not very much. But if s is a complex variable, a whole new set of tools and machinery opens up to you, and all of a sudden this becomes a really powerful tool. In fact, it leads ultimately to a kind of formula for the number of primes out to x, or as it's usually organized, one of the weighted prime counting functions that I've described. Riemann made a number of discoveries about this function of s, which he called zeta of s. That name has also stuck. Indeed, this is universally known as the Riemann zeta function. The first observation was that the zeta function well, I should say it this way. The infinite series up here and also the infinite product converge now when the real part of the complex number s is greater than or equal to 1. Let me you probably use this, and we can come back to this in a second here. Here's a brief model of the complex plane. This is the same complex plane that has come up in some of the other talks. Right here, for example, is the number whose real part is 2 and whose imaginary part is 10. So that point I identify with the complex number 2 plus 10i. The other points, of course, are organized in a similar fashion. And this is only part of the complex plane, obviously. There's also complex plane down below and off to the left and so forth. But this is enough for my purposes here. Riemann observed that the function he called the zeta function converges in this half plane. So this is all of the complex numbers whose real part is bigger than 1. Remember, Euler understood this as a function of the real variable. So Euler got it to define something only along the positive real axes here bigger than 1. Riemann is going out into the complex plane. Riemann also discovered, and I'll have to be a little brief about these things because they get a little technical, that the zeta function has what's called an analytic continuation into the whole complex plane. There's what's called a singularity at 1, but that's an understood sort of phenomenon. And what that means is that although these expressions no longer define the zeta function out in the rest of the complex plane, that's okay. There are other expressions which do define the zeta function, and this extension process is unique. There's only one way to extend it into the rest of the complex plane and retain the property of being an analytic function. Riemann also discovered a relationship between the value of the zeta function at s and the value at the point 1 minus s. Then he noticed, and now he was a little more vague and didn't really supply proofs. He definitely proved the functional equation in the analytic continuation, but number 3 he was a little vague about. He observed that the zeta function occasionally takes the value 0, not in the part of the complex plane where it's defined in this fashion, but over on the left-hand side of the complex plane at -2, -4, and -6, and -8, and so forth. Those are called the trivial zeros because they're easy to find. Set those aside. I'll just talk almost as if they don't exist. The trivial zeros don't play much of a role. They have an important role, but we understand them completely. They're not mysterious, and so we can set them aside for the purposes of this discussion. More importantly, he discovered that there were infinitely many zeros in the region of the complex plane described here in this set. This is the set where the real part of sigma is between 0 and 1. So if we go back to the complex plane here, what he discovered is that in this region in the complex plane, which I'm shading in blue, the so-called critical strip, there were going to be infinitely many zeros. In other words, you take a point in here and you plug it into the zeta function and you see if it comes up with a value 0. And that's going to happen infinitely often for a certain set of points in this region. You might ask why the 0 is relevant in the first place. That's a good question, and it's going to be answered here in a moment. But before we get to the precise reason, Riemann also indicated a rough argument why the number of zeros up to height capital T. So in other words, if beta plus I gamma is a complex number, which is a 0 of the zeta function, then, since I'm only talking about the non-trivial zeros, beta has to be between 0 and 1. And the number gamma, think of that as between 0 and a big number, capital T, which you can name. And then n of capital T is the number of zeros of the zeta function up to height capital T. And Riemann indicated that it must satisfy this approximate formula here. He was a little vague as to what this is supposed to mean, but we now know, in fact, that n of t is exactly equal to that, plus a pretty small expression that has to get added on as a sort of correction factor. Now we come to one of his most spectacular discoveries. The reason that Riemann was interested in the zeros is exactly these formulas. So Riemann sort of modified Chebyshev's weighted prime counting function and defined a different weighted prime counting function, which he called capital pi of x. So capital pi of x counts a 1 whenever you encounter a prime less than or equal to x. If you encounter the square of a prime, it counts 1/2. If you encounter the cube of a prime, it counts 1/3. So capital pi of x is a pretty good approximation to little pi of x, which just counts primes. You can do this with little pi of x too, but the formulas become very complicated, and it's better to use a weighted function. What Riemann discovered was this astonishing formula. The number of primes up to x, but counted in this weighted fashion, is given by, here is Gauss's logarithmic integral of function, which comes up for a very natural reason that Gauss could not conceivably have imagined. It comes up for a technical complex analysis region that was a reason that Gauss did not have the ability to comprehend, let's just say. And I don't mean to take anything away from him. Gauss realized that Li of x was the right function when he was 15 years old. But it seems borderline clairvoyance that, in fact, Riemann's analytical machinery revealed that Li of x was, in fact, right on the money. That was exactly what should be used there. Nothing else is as good. Riemann went on to form a sum over the zeros row. These are the non-trivial zeros of the Riemann zeta function. They appear here and make, well, it's a calculus type function, but it's a little awkward to deal with. Well, log 2 is just a constant. And then this object down at the end here is a very small calculus type function that doesn't play too much of a role. It comes from the trivial zeros. Here's a formula that was later found by von Mangold, who proved rigorously Riemann's formula. This formula down here, this explicit formula, is for Chebyshev's psi function. And it's a lot easier to use in practice. This subject can get technically ferocious as it is, so any attempts to simplify matters usually should be used. In this particular case, psi of x is x, and then there's another sum over the zeros of the zeta function rho. Those are the non-trivial zeros. And you'll notice now that the expression which is occurring here is x to the rho over rho. That's a lot easier to handle than the logarithmic integral of x to the rho. They can both be done, but this leads to sort of easier going. Now, this is a sort of dream that must have been shocking for anybody to see for the first time, because the prime counting functions behave in an irregular, seemingly almost random way, indecipherable. No elementary approach, just using the integers and the definitions of primes, seems to be able to reveal to this day that the zeros of the zeta function, certain complex numbers, should come into play in describing this function. And yet Riemann worked through these details, reported the news in one 8-page paper that he wrote in 1859, and he didn't write another word about number theory. And this is probably one of, at least in my opinion, one of the most influential papers in number theory ever written. It took about 30 or 40 years for some of Riemann's ideas to actually get rigorous proofs, usually at the hands of others. There is one famous problem, and of course that's the subject of this evening's lecture, that Riemann left for the rest of us to work on. He writes, and now this requires a little interpretation. Riemann spoke about the function zeta 1/2 plus it. The zeros of the zeta function occur in the strip in the complex plane, where the real part is between 0 and 1. But if you make this little change of variables, that strip becomes a strip around the real axes. Riemann wrote, one finds, in fact, about this many real zeros. He's speaking there of the number of zeros that occur with real part equal to 1/2. So one finds, in fact, about this many real zeros within these bounds, and it is very probable that all the zeros are real. That's the Riemann hypothesis. So what he's saying is, it's very probable that the non-trivial zeros of the zeta function have real part equal to 1/2. So in other words, they all lie on the center line. Let's go back to my complex plane again. The blue region is the region where Riemann proved, in effect, that all the non-trivial zeros occur. There's more of the blue region down below, but this is enough for the purposes of my talk here. Riemann is now going beyond that and asserting that, in fact, if you look at the center line here, that, in fact, all the zeros occur on that center line. Well, let's take a look here at a little evidence. So here are the first 20 zeros of the Riemann zeta function. And you see that Riemann was right on the money. They're all on the half line. But the evidence gets better. Now, I can't, of course, produce too many zeros here in a short talk, but here are the zeros of the zeta function numbered 10 to the 12th plus 1 out through 10 to the 12th plus 20. And all the ones that came in between are on the half line, too. So far, he's doing great. Finally, and this is now right out at the end of modern computational methods, Here are the zeros of the zeta function, and I should thank Andrew Olitzko for most of this computer work. Here are the zeros of the zeta function between 10 to the 22nd plus 1 and the 10 to the 22nd plus 20th 0. You can see if you study these numbers that the zeros are going to be crawling along a little bit more slowly the further you get out. There isn't any discernible pattern here, except like the primes, there's a kind of an irregularity of detail. But then when you stand back and you look at a lot of them, they seem to kind of flow together more or less smoothly, more or less. Let me return to the explicit formula. The reason for studying the zeros, of course, as I said, is that we have a kind of magic tool here. Psi of x is the weighted prime counting function. And it's given by a kind of, well, it's similar to a Fourier series. There's a lot in common with the Fourier series, but it has some differences too, in which this sum appears, provides us with a series in which the zeros row of the zeta function appear. Now, psi of x, like pi of x, is constant between integers, indeed between prime powers. And so one might ask, if you were to just use, say, the first 500 zeros, or anyway, some subset of the zeros, and truncate this sum and make it a finite expression, and then you could compute an approximate graph of this psi function, one might ask what that looks like. Well, here's what it looks like. Now, this is a remarkable graph, because this number right down here is exactly log 2. I'm looking at the psi function, of course, in a region where there are no mysteries, down near 3, 4, and 5, and so on. You can also perform this activity further out for larger values of x, but then you need more zeros. So if you really want to see an accurate graph, I choose values of x that are relatively modest. The y value here is exactly log 2. Once I pass over 3, I get log 2 plus log 3. It's exactly that line. Once I pass beyond 4, 4 isn't a prime, but it's a prime power. So I got to add on another log 2, and that's exactly the right value. You'll notice, like a Fourier series, there's what's called a Gibbs phenomenon associated with these explicit formulas. As the function tries to change its status from one constant value to another constant value and approaches a discontinuity, it sort of gets ready to do that by fluctuating a little bit. Of course, we could dampen that down in various ways, but this exhibits exactly what happens when you truncate the approximate and make an approximate functional equation. Now, here are some statements which are equivalent to the Riemann hypothesis. So the first one is just the Riemann hypothesis, plain and simple. All the non-trivial zeros of the zeta function lie on the line real part of the 0 equal 1/2. But a consequence of that, or, if you want, an equivalent statement, would tell us that Gauss's original notion that pi of x is very nicely approximated by the logarithmic integral of x can be made in this precise fashion. So for every positive number epsilon, no matter how small, there's a constant that can be computed from epsilon, such that the distance from the approximation Li of x to pi of x is, well, roughly speaking, square root of x. It's a little bit worse than that. But roughly speaking, the difference is about square root of x. Exactly the same statement can be applied to the approximation of the weighted prime counting function found by Chebyshev. That's well approximated by x. And again, the difference is roughly square root of x. Here's one down at the bottom which indicates that you could change the Riemann hypothesis what seems like in a rather drastic way and still make a statement which turns out actually to be equivalent to it. Define the Möbius function in this fashion. It's minus 1 to the m if n has exactly m distinct prime factors and 0 otherwise. And so when you take a look at mu of n, you see what appears to be random choices of plus 1, minus 1, and zeros without any particular pattern at all. The Riemann hypothesis would follow if you can prove that the value of this limit exists. The series converges, but conditionally. The Riemann hypothesis would follow if you can prove that the value of this limit exists for all values of the real parameter sigma, which are bigger than a half. And if the Riemann hypothesis is true, then this limit exists for exactly those values of sigma. Now, I have to also say that while you can continue this with a list of things that seem to involve the zeta function in odd ways and make equivalent statements to the prime number theorem, as a practical matter, nobody has really used anything like this to say anything particularly deep about the Riemann hypothesis, other than this is an equivalent formulation of it. But it doesn't seem to be, shall we say, a useful equivalent formulation, not so far anyway. Now, let me continue here with some results very briefly that I'll report after Riemann. You recall on some of the previous slides, in particular the one concerning Legendre and Gauss, that they had both more or less indicated that probably the ratio pi of x over Li of x converges to 1. Chebyshev proved, remember, that if it converges at all, it's got to converge to 1, but Chebyshev wasn't able to actually prove that the limit exists. This problem was an important one at the end of the 19th century that was finally solved by Hadamard and Delavalle-Poisson. Here's a picture of Jacques Hadamard. And this became known as the prime number theorem. And it remains a kind of a benchmark. If you have some ideas about how to attack problems about primes, especially the estimates for pi of x, a good test is, can you prove with your methods and your ideas the prime number theorem? Can you prove this? Lots of times you can't. And so that says that your method is perhaps in need of more work. But if you can prove this, then people are going to be interested. You got to have a fairly good idea to prove this fact in some fashion. Now, of course, if your method is just to repeat the known proofs, which involve the crucial fact that zeta 1 plus it is not 0, so that's no zeros on the 1 line. That's a long ways from the Riemann hypothesis, but it's a little information about the zeros. The analytic proofs for a long time that were known up until about the 1940s all went through that step. So they were all, in a sense, the same proof. More about that in a minute. Let me also remind you of the seemingly good conjecture that the logarithmic integral of x is always bigger than pi of x. I said that wasn't really true, and that was established by Littlewood in 1914, although Gauss and Riemann had both voiced the opinion, Riemann and sort of indirectly, that probably Li of x was always bigger than pi of x. In 1933, in spite of the date I've indicated here, in 1933, Skews, who was a South African mathematician, took on the problem of establishing an actual numerical value for Littlewood's theorem. And he came up with this fantastic number, which is called Skew's number. He announced this in 1933, although the result was never published until 1955. I don't know why. In 1933, when G.H. Hardy saw this, he remarked that it seemed that Skew's number was the largest number that had ever actually been used with a definite purpose. But it seems that with modern technology, and in particular knowledge of the first zeros, you can improve this rather a lot. You can go all the way down to merely 10 to the power 371. As far as I know, this is the greatest sharpening of an upper bound in the history of mathematics. If you think about the size of Skew's number and experiment a little bit, you will be impressed. Okay, I just have a couple more remarks here about recent developments. You know, in the 20th century, there are thousands of papers on prime numbers, and it's not possible to mention many of them, even some of the best ones, because a certain amount of technical development has to be made. And so I can only speak about a few things that, well, can be related at least to objects that have already occurred here. The first I want to mention is a result due to Attlee-Selberg. I have a picture of Selberg here. And Selberg proved that, in fact, a positive proportion of the zeros of the zeta function occur on the half-line. That's quite a ways from the Riemann hypothesis, but it's encouraging. So the precise statement is that if n0 of t is the number of zeros up to height t, which have actually real part equal to a half, so they're on the central line, and n of t, as before, is the actual number of all the zeros up to height t, then it turns out there's a positive constant c, such that the number of zeros that are on the half-line is actually greater than or equal to a constant times the total number of zeros. So that constant is the proportion of zeros that you can say are on the half-line. The c in Selberg's original result was quite small, but in modern times the c has been increased, and the best result now known is that you can take c equal to 2/5. So one way to say it would be that 40% of the zeros are in fact on the half-line. Even if we proved 100% of the zeros were on the half-line, that's not the Riemann hypothesis. There might just be one or two exceptions that are lost in the asymptotics here. But still, it's encouraging. Another event connected to Selberg and also to Paul Erdős occurred in 1948. And this was quite a surprise to experts in the field when they found a proof of the prime number theorem. Remember, I said that was sort of the benchmark theorem. If you can get that, you must have introduced a good idea. It had long been believed that it was, in some sense, impossible to prove the prime number theorem without making use of the zeta function. But Selberg and Erdős showed that that was not how things work. They found a proof of the prime number theorem that just used calculus. No zeta function appears in the proof. And it's not a fake. I mean, there's no substitute. You're not using functions that are sort of disguised versions of the zeta function. It's really different. This was quite a surprise, and for a long time, well, maybe 20, 25 years, it was a sort of a popular idea that perhaps you could prove the Riemann hypothesis by studying the primes directly without the zeta function, and then produce one of the good estimates that I showed on a previous transparency, which would then imply the Riemann hypothesis. And once you've got all the zeros on the half-line, then the Riemann zeta function is a much more powerful tool. In a sense, it sort of makes sense that such an attack on those might work. This view, I think, in modern times is not so popular. Anyway, it was popular for a while, but I don't think too many people would argue that today. Well, this may be partly because there's a new popular approach that was discovered by Hugh Montgomery. Now, this is probably the most technically complicated thing that I have here to describe. Let me also show you a picture of Erdős here. Well, so when Hugh was a graduate student, he was thinking about the statistical distribution of the zeros of the zeta function. And this is kind of a rough description. What he did was he studied the distances between the zeros and assumed that the Riemann hypothesis is true. Not just the gaps between consecutive zeros, as occurred on my list, but all the different lengths that you can make by taking the difference between two zeros, or really between the imaginary parts of the zeros. You can leave the half part out of it. And he discovered, roughly speaking, that the Fourier transform of this distribution function could be identified. And it was a sort of elementary looking thing. And then in a memorable conversation that he had at the Institute for Advanced Study with the physicist Freeman Dyson, well, he was explaining his result to Dyson, and Dyson said, oh, of course, the limiting function is, and then Dyson explained to Hugh what it must be. Naturally, he was astounded. And he said, how did you know? Well, he said, you're computing the pair correlation function. It is also the pair correlation function of the eigenvalue of a random Hermitian matrix. Wow. That was a new connection between the zeros of the zeta function and ideas that had only been dimly thought about in the past, to sort of compactify what's happened. Hilbert and Polya, earlier in the 20th century, suggested the attractive possibility that the zeros of the zeta function are the eigenvalues of some operator. They didn't say what operator. They didn't say what space this operator is supposed to act on. But you can imagine that it's just a matrix, let's say, but an infinite matrix. And what Montgomery discovered was that, well, if you imagine that there is such an infinite matrix, and you imagine that the ij entry of the matrix is formed by some process that involves the distribution of primes, you might, from all I've said here this evening, think that those entries, the ij entry in the matrix, probably looks kind of random. And you might look at the matrix and notice that the ji entry is the complex conjugate of the ij entry. Therefore, the matrix is Hermitian. Therefore, all of its eigenvalues are real, and therefore the Riemann hypothesis is a theorem. There's a lot of imagining there. But, well, that's the sort of thing that makes good mathematical research. And I think that's about all I have to say. Thank you. Any questions? Yes?
When you gave the numerical results, first two zeros, there's some error bars there. Now, why are the error bars entirely in the imaginary direction but not in the real direction?
Oh, it's known that they all fall on the half-line because you can count the number of zeros that are on the half-line because you can make a real-valued function that will cross the x-axis exactly where there's a zero of the zeta function. So you can count the number of zeros on the half-line up to height t, and the von Mangel formula gives you a formula for the number of zeros of any sort whatsoever up to height t, and they match all the way along up to 10 to the 22nd. Yeah. That's a good question. Yeah?
So how many different proofs of the prime number theorem have been made?
Well, I guess 4 is probably a reasonable statement, although, yeah, 4, there are some similarity, 2 of them kind of based on similar ideas. Yeah, there's the analytic proof that uses the zeta function, and there are many ways of doing that, but at some point you got to use zeta 1 plus it, not 0. And then there's the original Selberg idea. And there are 2 others that come from very clever ideas introduced to sieve theory, which normally doesn't produce asymptotics. It normally just produces inequalities. Well, so 3 or 4, depending on how you want to count. Any other questions? Yes?
Regarding the last idea about computing the eigenvalues,
Yes?
do they construct approximate operators so you can reproduce part of the zeros?
I'm not aware of any experiments in that direction so far. It's a plausible thing to try. Yeah, the trouble, I think, is that you need some kind of scheme by which you're going to take the primes and build the operator. And there are, endless, it's an open thing. How do you do that? Well, well, to answer your question, it's a plausible thing to try, but to the best of my knowledge, nothing too tangible has gone on in that direction so far. Yeah.
The Laplacian on the fundamental domain of the modular group.
Yes?
That's the transformal calculation perspective.
Oh, well. Okay, there's some computational justification for this point of view, but I mean, I don't know of any theorems in this direction. No. Are there any other questions? Yeah.
Where the Riemann hypothesis proved false, would it have any real far-reaching kind of
Yeah, you bet it would. Yeah, either way would be a terrific result. It seems clear that it requires, I don't know quite how to say it, but it probably requires mathematics we don't know how to articulate today, evidently. I don't think it's just a matter of using what we know in a clever way. I think it requires another Riemann idea, because very smart people have thought about it for quite a while. And there are various ways of measuring progress, and they don't stack up too well, really. The zero-free region of the critical strip in 1906 is insignificantly different today. It's a little better than it was in 1906 because of tremendous, ingenious work on exponential sums, but it doesn't have any deep implications, really, other than it shows the cleverness of people who work in the field. But, I mean, it's still about the same as it was in 1906. Now, Selberg's result on the proportion of zeros and the refinements thereof are evidence in favor of it. The computation is certainly evidence in favor of it. There are also the so-called Weil-Riemann hypotheses, which are a little technical to explain, but there are objects similar to the Riemann zeta function that come from the theory of curves over finite fields, and properly interpreted, the Riemann hypothesis is a theorem in those cases. But those objects, from an analytical point of view, are much, much simpler things to work with than the zeta function is.
But they have the operator in those cases also.
Yeah, right.
And just finite dimensional.
Yeah.
Well, all right, one more.
This is kind of a simplistic question, I guess, but apart from the wonderful things that can fall out of trying to prove this or proving it, does the Riemann hypothesis have any, or the proving of it, have any implications for actually finding primes or proving a number's prime?
Well, I see. Not in a real simple, direct way. It does have a lot of implications, some of which are fairly technical to describe. The thing I chose to do here was to discuss its implications for the prime counting functions, because that was historically what I think Riemann was after. And I think it still remains maybe the simplest basic number theory problem that connects to the zeta function. But the Riemann hypothesis, for example, has been discovered as an important problem in mathematical physics. So there are a lot of different connections with other things. Now, you specifically said methods for deciding if an integer is prime or not.
It's the most simplistic.
Yeah, as a practical matter, I don't. Maybe if you have just the right question of that sort, yes. But naively, I don't think there's an immediate connection. Yeah.
Some extended Riemann hypothesis holds that primality can be decided with deterministic probability.
Oh, now that's a different issue. Yeah, of course. Yeah.
Well, don't forget to watch for the announcements next fall, and maybe it's time to go and have some refreshments now.